All right, why don't we get started here? So we've started on code generation. Now I should explain, since the Project 3 skeleton is out and you're probably wondering about the relationship between lectures and skeleton, I should point out that the skeleton provides you with some utilities for producing assembly language. It doesn't introduce the abstraction of an intermediate language, but the point of these lectures is that, well, it might be a good idea for you to introduce one, although you don't have to. So, for example, it might be easier for you to think along the lines in this slide here, for example, and then and it's easy enough to do. Basically it means that you have functions whose purpose is to generate these various instructions, like assign immediate value to register and so forth. And then the implementation of those functions simply generates the appropriate assembly language code. That's one way to do it. But in any case, the idea here is just to describe this very common abstraction used in compilers. And just another example of the kind of abstraction that we do when we're building large systems. The purpose of having an abstract assembly language is, first of all, that you can put off thinking about registers. That's kind of useful. And secondly, you can keep things. You don't have to worry about the details of machine language format and so forth. It's all that all is hidden and handled separately. So at the time that you're generating code for a def or for an if, you can think in terms that are appropriate for that particular construct. So here is an example of a translation of the Fibonacci program. So the translation is down there at the bottom. So into this 3 address code. So we start with some sort of function prologue, whatever that has to be, the code that enters the function. And then you see what happens is that we go along basically in a sort of depth first traversal of the tree, left-right traversal or something like that. And so the first thing we do is we evaluate x, and we evaluate x by stuffing it into a register, allocating and stuffing it into a register. And if you go back through the preceding slides that describe how we do each of these, how we handle identifiers, how we handle equalities, you'll see how that works. That is to say, if you look at the preceding slides, you'll see how they lead to this code, for the most part anyway. We compare that. If the two sides are not equal, then we branch to a label that we haven't yet defined, but we say there's going to be a label that we branch to. And we put the result of the if into register 2. That is, we've chosen register 2 to hold the result of the if. And then, having done that, we branch down to the end of the if statement, which is right over here, that returns the value of the if statement. Okay, so assuming on the other hand that that's what happens if R1 is equal to R1, that is to say x is equal to 1. If R1 is not equal to 1, then we come down here into the else branch, and you see that we first of all evaluate x again. We compare it with 2. If the result is, if that's true, then the result is we put the result of this if statement, this inner if statement, into register 4, and we come down here and put that into the result. Put register 4 into the result of the outer if statement, and then return that, and so forth. This is pretty straightforward. Here is function calls. Here are function calls. We evaluate x. We compute x minus 1. That's right here. We push that as a parameter. Then we call the Fibonacci program with one parameter. And the results of this statement we'll put into register 7. We'll say that we'll take that from some return register, whatever that is. That's just an abstract quantity here. On the IA36, there actually is a register. It's for integer and pointer quantities, which is the EAX, the extended accumulator register. And then we do the same thing for for the second fib. We add the results together, R7 plus RRET, and we put the results into R4, which, as you may recall, is where we were putting the results of the inner if statement. That then goes into R2 and outward, and we're done. Now, you look at this and you say, boy, wow, that's a lot of registers. I mean, gosh, do you really need 10 registers to evaluate something like this? I bet I could do better than that. Well, first of all, of course, you understand this is intermediate language, so these aren't real registers, and necessarily, first of all. And second of all, even if they are real registers, they don't have to be different registers. So the code generation could be really clever and say, well, I know, for example, right here at this point, where I do, let's see, where's a good one? Okay, so up here, where I compute R6 and then push it. As soon as I push R6, I no longer need it. So I can, so in principle, I could reuse R6, whatever I've used for R6, I could reuse it for other things. Here, where I do R6 gets R5 minus 1, I no longer use R5. So in principle, I could simply make R5 be the same as R6. And that would all collapse. And it turns out that when you're done with this, I only need a few registers. Okay, so anyway, this is all abstract. So first thing you have to understand is that the fact that it looks like I'm using 10 registers doesn't mean that I really am using 10 registers in the physical program that I generate. Furthermore, the fact that I'm calling them registers doesn't even necessarily mean that they're registers. I could decide that when in converting intermediate language to underlying language, I could decide, well, maybe I'll just put everything on the stack. I'll just allocate a compiler temporary, put it in there, everything's fine. So these are all viable. These are all perfectly viable options, and this two-level thing has the advantage that this code, if you look at the preceding slides, this code is really quite easy to generate. And it's not very good, but you can imagine, and this is the usual pattern. We generate this bad code, and then we go back and, without knowing anything about the original program, just looking at the code that we've generated, we go back and we improve it in various ways. We choose better registers, we put things together, we just choose whether things are going to be in registers or not, we do all kinds of things like that. And then generate assembly language. So that's a usual path. Again, for Project 3, I'm leaving this quite open, so you can, last year I actually had explicitly two different things. So Project 3, you did two parts. You did the generate machine language, generate the intermediate language, but I decided perhaps that was getting going a little too far. So I'll let you be more concrete, while inviting you to consider the possibility that maybe your code generator routines ought to call something a little bit more abstract and then deal with that later. Okay, so this is basically what we've done now is we've looked at the concept of intermediate code, of three-address code in particular, and as stack machines, that's another alternative, as a representation, as a sort of a stepping stone, a representation toward the translation of source program to machine language. And it's just another illustration of this idea of the theme throughout all of our computer science programming course offerings of abstraction. The purpose of this abstraction is to do things in small, understandable pieces, number one. Number two, to give you a way of to give you a way of leveraging one implementation of Python on one machine to other machines. Because of course, if at some stage in the process you generate this code, then this code could be translated into machine language for any machine you want. The process is different for each machine, but at least you could use the same pattern here to generate the code. So for a number of software engineering reasons, this is an interesting and often pursued approach. Okay, so I think that wraps that part up. And let's take a look here. For your information, okay, so I'm sure many of you are anxious about the test. As usual, we keep you on tenterhooks for some time. Our TAs are in the process of doing research, so it will be a little while before we get these things completely done, but they will be done. That's these Macs. You know, if you touch too much at once, everything goes crazy. There we go. Yes, here we go. All right. Okay. So, questions so far, or about the project? The runtime. Oh, yes, that's right. The runtime library at the moment, there's just this tiny little skeleton. You will see a bunch more materialize pretty quickly, so you'll know what the runtime system is doing for you. Do be sure to look at it. Do be sure, please, not to duplicate unnecessarily things that we're already doing for you. This is one reason for looking carefully at the skeleton and seeing what we've done, because there's nothing worse than spending hours and hours and hours doing things, and then you suddenly discover, oh, I never looked inside this file. What's that? Oh no, I've already done that. You know, and then, of course, turning around and saying, oh, why does the professor give us so much work? You know, or why does he do all this work and not tell us about it, or something like that? Well, let's not have that happen. So anyway, the runtime system we filled in, it does a great deal for you. I think I will be doing a little bit of rearrangement, I think, because some of you may want to modify the runtime system, and you can do that. It's fine. It's written in C++. You can fiddle with it. And I just have to make sure that when the autograder runs, it uses your version of it. Naturally, you better add that to your project if you're going to do that, but that is an option. Right. Hang on. There was something else I was going to say about that. For example, one group was thinking to itself that, gee, one way of doing this is to simply unparse everything into Python and then call the Python interpreter on it. I will notice if you do that, however. So please, let's try to keep things clean. All right. And by the way, to be honest, the way people would normally do this, they were doing a breadboard or prototype implementation of executable Python, directly executable, or machine code Python. The first thing they'd probably do is actually translate it to C, and then use the C compiler. That's a very common thing, and it makes unnecessary a lot of stuff. And in fact, I mean, that's actually in real life, that's a perfectly legitimate thing to do. But I did want to have you push this through to the bottom so that you can see everything. Okay, so let's take a look at this next step, then the final step, which is translating from this abstraction, this 3-address code, or directly in your code, translating to the actual machine language. And what this does, and the concepts that we introduce at this point are the things, the main problem here, actually, when you come right down to it, is the handling of registers. So Whoops, oh, why don't I put this on the full screen? So we have dozens of registers. We want to know what those really mean. And why do we have dozens of virtual registers? Because it's convenient. What that means is that if you're going to generate code directly, you want to somehow have a nice set of abstractions for allocating registers. If you're not going to allocate virtual registers, you'll have to allocate real registers, and you better do that in some reasonable fashion that doesn't require you to write huge amounts of code every single time you need a new register. You'll want some set of abstractions that give you that possibility. So we'll be covering that. Now the concepts here. Now, first of all, why are we doing this? Well, there are various reasons. First of all, many machines tend to require that certain operands be staged to their registers first. And second of all, and one good reason for this is just speed. The registers are the fastest piece of the architecture that you can access. And so historically one tries to put everything there. So let's just see what's involved in doing that. Now, one of the little roadblocks that gets thrown in our way by architectures is they will often reserve certain registers for special purposes. And this is painful, but that's the way it goes. And so one good strategy that you can use is you'll choose a few registers that you are pretty sure you can claim. And then for everything else, you'll put things in compiler temporaries. So you'll have your allocation stuff will generate memory operands quite often as much as registers. But you'll see that when you come to it. Okay, so a simple strategy here is to do everything is a local, what we call local register allocation. And that means that we handle the allocation of registers within individual basic blocks, so-called. We'll say what those are. Well, as it says here, these are sequences of code without branches in them except at the end, so that you start at the beginning, you go all the way through, and you know the order of instructions is therefore just exactly as it is in the block. There's no complication caused by loops or conditionals or anything like that. And then when we get to the end of each block, we'll take all the registers, any registers that are still needed, whose values are still needed, and we'll just stick them into compiler temporaries. And that's where they'll live sort of between basic blocks. And this gives you a little bit of use of the registers. So if you've got long basic blocks especially, you'll be keeping values in registers for as long as you can, and that's kind of nice. Okay, now one thing that you have to do if you want to do this well is that it's good to know when a register is alive and dead. This is the terminology. Now, who knows where this terminology came? Why they didn't just say no longer needed or irrelevant or something. Maybe the word is too long. I'm not sure, but they chose alive and dead, which always sounds violent to some people. I mean, think about it. Your value is no longer needed, therefore, bang. I mean, terrible. But I can't help it. I didn't make the terminology. All right, so when a register is no longer needed, we say that it is dead. No longer needed means that no matter how you go, how you proceed from that point where the register dies in the program, you will never fetch its value. You will never need its value or that particular value that it contains at that point at any further along any path in the program. We'll talk about that in detail later. Now, of course, when you're generating code, the way that in the preceding slides, it will occur to you that because we are generating fresh registers each time, you'll generally be able to tell immediately when a register dies. For example, if you, the code for generating the register that gives you an identifier, if you fetch that identifier and then you use it immediately in a binary operation, you know that at that point, because of the way that you've written this code, this naive code generator, you know at that point you no longer need it. Because you're not going to, because the way that the code generator works is you load something and then you immediately use it. So there might be a kludgy, well, let's say a heuristic way that you can do this fairly systematically without doing any careful analysis. But more on that later. So right now, let's assume also that for every register that you allocate, you have a compiler temporary that you can use if there is not room, if there is no register that we can really, no physical register that we can actually assign to it. So basically, the picture then is every single quantity and intermediate variable in the program has some memory location on the stack. And what you try to do is use registers as a sort of a cache to avoid fetching or storing memory there as much as you can. So that's the scenario here. All right. So here's a simple technique. It's from A. Hossetti and Ullman. It is written assuming that. It is written assuming, I believe, yes, here we go. No, it doesn't, I'm sorry, it doesn't have to assume that. So here's how it works. We imagine that we have an instruction such as x gets y op z. In other words, an instruction that changes some value on the left side and uses some operands on the right side. So binary operations, function calls, function calls with a bunch of parameters, number of things like that. Now, if we already have assigned a register, if at the moment, as we're traversing our program, instruction by instruction, if at the moment we've already assigned a register to X, then fine. Everything's great, we just keep it, and that's great. So that's fine. So now, if Y is a register and is no longer needed, so otherwise, if X, we don't have a register for X, but Y is a register and is no longer needed, then we'll just reuse that register in X. We'll just, so we can reuse Y's register in X. That's fine. So that means that Y no longer has a register, X does. All right, fine. Now, if both of those fail, then we can look at our stock of available registers, see if there's any in there, any register that we haven't used, and we'll just use that for the register. All right, so we'll just take that, and of course we'll take it out of the available register so that we don't reuse it. And then assign that to X, that's fine. Now, otherwise, if there isn't another register to apply, and if in fact we're going to need a register to do this, then we will spill one of the registers. And then use its physical register for X, and otherwise, if all of this fails, then we'll just leave X in memory. So that's how we will allocate registers to all of these things. Now, the important thing to understand is, or the assumption behind this code, is that you will first execute this to assign registers, and then you will generate the machine code for this instruction. So, for example, and this may be a little bit confusing, but that means that right here, when you reassign the register from Y or Z, for the moment, just for a second, the register or the values will still be in Y or Z, so that you can use them. But immediately, and you'll pull them out, but you'll stick them into X immediately. So you're sort of anticipating what's going to happen as soon as you do the operation. All right. So with this scheme, this is a scheme that you can use as you're going through generating code. Now, if you're doing it directly, if you're doing this code generation directly, then probably what's going to happen is that at that point in your code gen routines where you're generate an op. Oh yes, sorry.
I have a question. The second elif case is op requires a register.
Yes.
What op require a register and which ones don't?
Well, it might be the op requires a register. Oh yes. So the problem is that there are some operands that require that there are some operators that require that operands be in a register, right? There are on some machines, for example, on the VAX, the old VAX, you could have cases where all of the operands and the result were in memory. Good old CISC machines, you know. But if you do need a register to do it, then you will have to free one up for doing the operation. So, for example, if it's something like x gets x plus 1, or y gets x plus 1, you could say, I don't need x anymore, or I will need x in the future, but unfortunately, I don't have room for some reason, so I will just say that after this instruction, y now has x's register. I won't do anything, but I'll say that y has x's register, and I will now perform the operation on x, on the register that used to be x, and I'll just call that y from now on. That's sort of how it works. Okay, so this is a simple-minded scheme. It works in basic blocks. It does, relative to what a full-blown production optimizing compiler does, it does an awful lot, it keeps an awful lot in memory. But it's simple and it works pretty well. Okay, so now how about, it works for our purposes, let's put it that way. Now, let's consider now the details of the function prolog and epilogue so that we understand what these are. Now, I'm sorry, I keep switching back between Intel and AT&T format, so at each point I will try to be careful to explain what is going to where. So we've looked at this code before. It consists of the standard thing sequence in the IE32 is you save the old frame pointer, the base pointer, what they call the base pointer, by pushing it onto the stack. You then set a new base pointer by to be the current stack pointer. And then you allocate space on the stack for all the local variables you need by subtracting, since the stack in this machine goes towards smaller addresses, by subtracting some quantity k, which accounts for all that space. And now, from now on, you're able to reference local variables as offsets, negative offsets actually, from the base pointer. So that's pretty simple. Then it is traditional, it's conventional, that when you're returning a scalar value, an integer or a pointer, that you, or character or Boolean, that sort of thing, that you put it into this, there's one register that you generally use, EAX, as it's called. So you make sure you arrange for your result to go there at the time you come to the end, and then you execute this sequence, leave ret. Leave is just, it may just be I think it's just a synonym for something in the assembler. I'm not sure, but its purpose is, but what it does is to pull go indirectly off the base pointer and pull that value back into the base pointer. So in other words, it unwinds the stack. It changes the dynamic. It follows the dynamic link to get the old base pointer back. And then it does, and at the same time it pops off at the same time it pops the stack pointer back to where it was pops the stack pointer to where it was right here, right before we did all of this. And now the ret instruction pops the return address off the stack and returns to that. That's the sequence. Right? So that's pretty pretty straightforward, and that's it. I mean, basically that's the calling sequence. There are a few extra details, but this is the main thing. Okay. All right. So at this point, why don't we? I think we'd better take a brief break before we push on. Any other questions, or has everyone? Of course, you've all started planning Project 3. I hope, by the way, that you've noticed that Project 3 includes a component where I'm asking for a presentation or a exposition, if you will, of the compiler. So that means I'm asking you to look at I'm asking you to sort of give me an internals document. And I'd like you to try to do a serious job on this. That means, among other things, that even if you're using my skeleton, just because you're using my skeleton, if you are, doesn't mean that you don't have to explain what's in it. So this means that this is my way of trying to see to it that you actually understand what it is you're dealing with. So whether you write it yourself or whether you're using my stuff, I want you, if you're using my stuff, then I want you to explain to me how my stuff works. And as usual, this is your opportunity to practice your communication skills, or your written communication skills. So let's hope that works. Okay, and of course, this is something that does not have to be left till the last minute, right? All right, so better to understand things early on. Okay, fine. Why don't we take a break?
On this right here, why don't we check for Z as well? If Z is like, why isn't there another?
They're making I should have said, they're actually making the assumption here that Z is. They're making the assumption that that you've got a machine where if you're going to jump on top of a register, it's going to be register Y. In other words, that you won't really have the opportunity to use Z. I think that's probably their explanation. Let me see. Does that make sense? They're assuming that you have. Let's see how this works. So I have something like this. Now, there are two kinds of machines. There's the kind of machine where this variable here is, there's the kind of machine where this variable here, where there are actually three operands, and they can all be separate. They can all be different. And then there's the kind of machine, which is the one I think they're talking about, where this operand and this operand might be the same because the operation actually has two operands, namely the one that you're operating on, and then the thing that you're adding to it. So like the IA32, where you don't have an R1 gets R2 plus R3, you have a add this operand to R2.
Oh, so the add instruction itself only has two operands.
Right. So I think they're going. I think that's what they're pursuing, and so they're assuming that it is this one. That's the one that you want to. That's a target for reuse.
So it'd be like R1 plus equals like R2 or something.
Yeah.
Oh, I see.
Yeah.
Okay.
I think that's the idea. It's, right.
But in that case where we do have 3 operands, we could in theory just
Yeah,
check
sure.
Z.
Yeah. You have more options in that case. That's true. Yeah.
We have a problem from allocations.
Uh-huh.
So my understanding is that we need to use a framework. So if we have an integer, let's say x equal to an int, it's actually referring to a pi int.
Yeah.
So, but let's say if we have this pi list, does that also refer? First of all, is the int allocated on the heap or is it on?
Yeah. Well, yes, except that the runtime is clever about that. And if you have, since ints are immutable, if you have 2 instances of 5, for example, generated independently, the runtime will give you the same object for them.
Okay.
So it's not exactly a new allocation each time.
Let's say we have x colon this equals, and then like a bracket expression.
Uh-huh.
Would that be allocated on the heap or on the stack?
Oh yes, all of the lists and tuples and so forth, everything will be on the heap basically.
But are we responsible for calling the heap allocations or?
You're responsible for calling the heap allocations, but I'm writing the heap allocations.
But and we know what to call. We will know what to call.
Oh yeah. That's it's all. I'm going to release at least the headers of everything in the runtime system today, so you'll see what the names of the functions are. It's just a bunch of functions, and you can call directly.
And we're supposed to keep the pointer on the stack.
Which pointer?
The pointer to the object. So if we have x equals 5.
I don't care where you put the pointer where. It doesn't matter where you keep it, on the stack, in a register, in a temporary. I don't understand. But
I think we're.
anyway, yeah.
Yeah.
All right. Let us recommence here. So again, this is just a reprise of what we've been through before. It is convenient for a number of reasons. It's often convenient for a number of reasons to use a stack pointer, a base pointer, a frame pointer, to compute or to hold the address, the base address for local variables and parameters. So I'm going to. I'll use some assumption like this. I think look at these figures, and I think I'm sort of wondering if they're wrong. So on the IA32, for example, to access parameter I, numbering from 0, we will look at the frame pointer plus some constant multiple times it's indexed basically by the parameter number. Now, I believe it is the case that on the IA32, we'll use this first thing, K1, will be, I really should use this, shouldn't I? K1 will be 4, because everything is 4 bytes. We're using quantities that are all 4 bytes long. And K2, which is sort of the first parameter, is 2. So why would that be? Why 2? Why do we when accessing a parameter, so parameters are positive offsets from the frame pointer, why are we going an additional 2? Yeah. That's right. So the dynamic link. The return address and the dynamic link. I haven't actually said anything about the static link. That's a separate thing. But right, the return address and the dynamic link are sitting there in the stack, so you have to skip those before you get to the parameters. All right. Now, and then the local variables are at negative offsets from all of this. And so, at least on this particular machine. So that's all very well. But now we come to this problem. So that takes care of local variables. Variables that are at the outer level, the statically allocated things, those are easy because they're in memory somewhere. So you've put them someplace. You've got a label. You just use the label. Everything's fine. The actual static address, everything, or the link time address, I should say, everything's fine. But what happens when we have a situation like this? We're inside this nested function f3, and we have to get at x1. So we're here. We call for x1, and it's way out here. And at this point, we don't know anything about the location of f1's frame. We don't know, for example, how far away it is from that is to say, f3's frame. So what do? And this is where the static link comes in. We're going to so the way that we're going to do this is that's interesting. How are we going to do this? Yes. So the way that we're going to do this is to fetch to follow static links down to the function in question. Now, I think I'm making some assumptions here that I should not be making. Now, the way that in this particular scheme, I see. So in this particular scheme, let's suppose that the static link. I said when we did this that the static link is in effect an extra parameter to the function. So let's first of all assume that that's what's happening. So it's an extra parameter to the function, an invisible parameter that you sort of know is there, and you carefully make sure you carefully push it and so forth. And that would put it at location 8 off the base pointer, sort of the position of the first parameter. So to get from f3 to f2, we would first of all load that base pointer within f3. We would load that base pointer, which gives me the frame pointer for f2. And now that I have the frame pointer for f2, I can get the frame pointer for f1 by following its static link. That's what this instruction does right here. And at that point, I can now get at the parameter x1, which will be at offset 12, assuming that I'm putting the base pointers, I'm putting the static links as the first parameters. Now, in our implementation, in fact, I'm going to update this slide because otherwise it's going to be confusing. In our particular implementation, we're going to follow the GNU convention, in which you actually pass the static link in a register. Register ECX, as a matter of fact, is what they use to pass the static link. And then you store it as a local variable in your stack frame. So I will put that alternative thing here. But here, the assumption is, for this slide, the assumption is that we are passing the static link as the first parameter. And this is then what you do. So the takeaway from this is that we will fetch x1 when we have to access x1. We will generate code like this to follow the static links and go back to the frame that contains x1, and then we will pick it up. That's the general idea. And so, how do we decide how many times to follow the static link? Well, we look at how deeply nested we are, and we look at how deeply nested the variable that we're after is, and we do an appropriate subtraction, and then we sit around and we try to avoid the off by 1 error by figuring out whether what a distance of 2 is supposed to mean, and we finally decide, oh, I guess it means that I do 2 fetches. Do 1 fetch to go back to f2, and then another fetch to go back to f1. So figure that. Okay, got that. So this is how we were going to deal. This is how, or one. This is a technique for dealing with the static link. We're going to do something slightly different for this project, but it's the same concept. You pass the static link as a parameter. You put it someplace. When you need to go back and access this, you simply follow the linked list and to go back and get it. Okay. But yes, this definitely needs a little bit of updating, which I will do before next time. And in the meantime, have a nice weekend.